Hello, friends. Now, as programmers, we can all agree upon something. Debugging, it's hard. But what if it wasn't? What if debugging could be easy, or at least easier? In this video, I show you guys how to use the scientific debugging method in order to make debugging a lot easier. Now, before we jump into scientific debugging, let's talk about how debugging is currently done. Well, there are different ways of doing it. One I like to call Stack Overflow debugging, where you encounter some error, you look at the error message, and you read it or you don't read the error message, and you copy paste that error message into Google, and hopefully there's a Stack Overflow article or some other article, maybe on Reddit, where some genius coder explains exactly why the error occurred and explains how to fix the error. This is an okay way of debugging, but one issue is that what if there is no Stack Overflow article or there is no Reddit article that helps you solve your bug? Then what do you do? Another form of debugging is using something like ChatGPT or some sort of LLM or AI. You sort of do the same thing. You get an error message and you copy paste that error message and put it into ChatGPT. And then ChatGPT will spit out a solution to your bug. It'll tell you how to fix it. This is also great, just LLMs sometimes can hallucinate. So you might get a answer that is incorrect. But that is a way of going about it. All right. So now let's jump into scientific debugging. Well, first we need to go over some terminologies. Let's define the term failure. Failure is an externally visible error. So, for example, you sort of run your code and then out pops the output, and that output is wrong. That's an externally visible error because you can visualize it. But for example, if some variable has the wrong value in the code, well, you can't see that. So it's not externally visible. That's not a failure. Next, I want to explain the cause and effect chain. So the way that a failure happens, well, you have some input, and that input is inputted into a program, some code. And that code processes the input and sets certain variables to different values. That's our first state. Then the code operates on those variables, making them have new values, and that's how we get our next state. And then the code operates on those variable values, and we get another state. And that happens again and again and again until we get an output. Now, what happens is sometimes the code has an error in it, what is known as a defect. And that results in a good state, a correct state, becoming a faulty state. You have a good state, faulty code, a defect operates on that good state to result in a faulty state, also known as a fault. That is the cause and effect chain. With the terminologies defined, we can now jump into the specifics of the scientific debugging method. So step one is that we have to observe a failure. And a failure is as described before, an externally visible error. Let's move on to step two, where using our failure, we create a hypothesis, which is simply an explanation of why the failure occurred, specifically using the cause and effect chain in our explanation. Now, some things about a hypothesis is that a hypothesis, it can be wrong. So for example, if you wanted, you could use something like ChatGPT or GitHub Copilot to help create a hypothesis for you. And it's okay if they hallucinate because a hypothesis can be wrong. Now, even if your hypothesis is correct, it can still be improved. For example, let's say your hypothesis in your explanation of the failure uses a state that's very down to the right of the cause and effect chain. Well, what you can do is to refine your explanation to create a new hypothesis, you can start using states that are farther left in the cause and effect chain because you're getting farther and farther away from the failure and getting closer and closer to the actual defect. Now, after making a hypothesis, we can move into step 3, where you make a prediction using your hypothesis. Now, a prediction is basically a consequence of your hypothesis being correct. And the goal with making a prediction is you are trying to disprove the hypothesis. Now, the next step, you created a prediction, it's time to test it. You can test your prediction, and if your prediction is correct, then you can move from step 4 all the way back to step 3, where you make a prediction. You can make another prediction to try to disprove your hypothesis, or you can move to step 2, where you create a even better, more refined hypothesis. And you can refine it as we discussed before, kind of shifting left on the cause and effect chain, getting farther away from the failure, moving closer and closer to the actual defect. Now, if your prediction is incorrect, then this allows you to actually reject your hypothesis. And you can move to step 2 to actually create a new hypothesis. Now, if you find that what you thought was a prediction is not really a consequence of the hypothesis being true, then you can move back to step 3 and create a new prediction. Now, just repeat these steps 2, 3, and 4, creating a hypothesis, making a prediction, testing your prediction, until you have come up with a diagnosis, a hypothesis that you cannot disprove, and that pinpoints a specific defect that is causing your failure. I wanted to provide a quick and easy example showing the scientific debugging process. So let me share my screen. So as you can see here, we have a simple program. It's supposed to add 5 numbers. I'll zoom in. And maybe you can easily spot the error, but let's kind of pretend that, the error wasn't as obvious. How would we debug this? Well, first of all, let's run the program, and we get 7. So we get 1 plus 2 plus 3 plus 4 plus 5, and our program prints 7. But this is not correct. The correct answer should be 5 plus 4, 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. So we should be getting 15, and we're getting 7. So this is a failure, an externally visible error. So what we can do is we can make a little document where we sort of keep track of failures, hypotheses, predictions, and the results of testing the predictions. So for example, we can do something like debugging dot md. And what we can do is we can keep track of our failure. We can do something like failure, and we can sort of visualize this here. We'll put this on the side. And we can say something like, we let's say I ran the following code. I can close this. And I received 7. I should have received 15. So this establishes the failure. And now we want to come up with a hypothesis for it. So we can do something like, we can put our first hypothesis, hypothesis 1 maybe, and we hypothesize. So as we know, we have the cause and effect chain. We have that, input causes a state, causes another state, causes another state, eventually causing an output. So the idea is our output was wrong. So the way we can understand it is that at some point we had a good state and a defect in our code turned that good state into a faulty or bad state, a fault, which caused another fault, which caused another fault, which caused another fault, which eventually caused our output to be wrong. So for our hypothesis, rather than immediately try to detect the defect, let's try just starting more to the right of our cause and effect chain. Let's sort of use a fault that is closer to our failure within our hypothesis. So for example, what is a problem, what is a fault that could have caused our error? Or what is some problem, what is some state that could have caused this error? Well, one state is that we could have had AB set to the wrong value. And if AB is set to the wrong value, this could have resulted in our calculation being incorrect. So what we can do is we can sort of put that as our hypothesis that AB was the wrong value. It was not 1 plus 2, which is equal to 3. This resulted in the calculation being incorrect. And then once we create this hypothesis, now we can come up with a prediction. So one prediction is as follows. So if this hypothesis is correct, AB was the wrong value, then if we print AB, we should see that it is not 3. So let's try that. Let's write that as our prediction. Our prediction is that if we print AB, then AB will not be 3. This is kind of a logical consequence of our hypothesis. Now, let's test our prediction. We can say results. And we test our prediction by adding a print statement on AB. And we can even put some text here. And let's print it. We get that AB is 3. So our prediction is incorrect. AB is 3. So then from this, we know that our hypothesis is rejected. So we can now move on to a different hypothesis. Let's try a new hypothesis. Hypothesis 2. Let's consider another state, another fault that could have propagated and caused our failure. Another fault is that, well, maybe AB was correct, maybe CD was incorrect. So what we can do is kind of do the same thing. Let's say CD was the wrong value. It wasn't 3 plus 4 is 7. Now, from this hypothesis, we can make the following prediction, similar to as we did before. We could say our prediction is that if we print CD, then CD will not be 7. And now let's look at the results. Let's see whether or not this prediction is correct or not. So what we can do is print CD. What we can do is print CD. We can do something like this, CD, and we can run this. And we can see that CD is not 7. It is -1. So our hypothesis, our prediction is correct. Our hypothesis is supported. Okay, so now we have a hypothesis that is supported. CD was the wrong value. This resulted in the calculation being incorrect. Now, let's try to go even further back along our cause and effect chain. So we have a state that is incorrect, and we know that that state sort of causes our output to be incorrect. But what could have caused that state to be incorrect? Was there a fault before that fault that caused that fault? Or was it a defect in the code that resulted in a correct state transforming into a fault, incorrect state? Let's examine the code. So we're looking at CD, and we know that CD is incorrect. What could have caused CD to be incorrect? Well, we see that we have C and D, and C minus D is not what we're looking for. We actually want C plus D. So this is our, what we think is the defect in our code. So we can now write that as our new hypothesis. We can say, and we are effectively refining our hypothesis too. We can say something like C and D are not added to one another. Instead, they are subtracted. Instead, D is subtracted from C. This results in CD having the wrong value. It was not 3 plus 4 is equal to 7. This resulted in the calculation being incorrect. So now that we have that hypothesis, we can come up with a prediction for this to see if this hypothesis is supported. So now our prediction is, well, C and D were not added together. which resulted in this error happening. So our prediction is that if we add C and D together, then the calculation will be correct. Now let's test out this prediction. Let's see if we add C and D together, do we actually get the right calculation? We run the code and we get the right result. We get 15. So our prediction is correct. Hypothesis 3 is supported. And not only is hypothesis 3 supported, well, we can consider it a diagnosis because it is a hypothesis. And of course, we could subject it to more predictions, but so far, we are unable to reject this hypothesis. And this hypothesis mentions a specific defect, a mistake in the code that is responsible for the failure. Here are just some final tips. What you should do is rather than try to remember all hypotheses and predictions and the results of whether or not the predictions are correct or not, rather than keeping all that information in your head, write stuff down. Keep a log. Make a little Google Doc or a MD file, Markdown file, and just record all your information there. Another tip is to make sure to read your error messages thoroughly. Don't just look at the error message and just copy paste it and put it into Google. Make sure you read it and understand it, and then make a hypothesis that can explain why that error message is occurring. Now, I want to give a huge shout out to the resource that really helped me learn about scientific debugging. It's called the Debugging Book by Professor Andreas Zeller. I will link the resource in the description below. Now, please let me know if you want me to make any more videos about scientific debugging, and I would be happy to share. Thank you so much.